So let's continue about subject number 18, the boundary layer condition. Before to start about this, the boundary layer modeling and its analysis, we need to read or to recall what we done before. First, we know that as we have a way of solving a condition of a flow by using Navier-Stokes equation, which is the most general one, and even it can generate and derive formulas for certain cases. Okay, and then not then, and it is taking in account any shear forces due to viscosity or any other forces as well. Okay, and we agreed that to get about the solution, you need a sufficient boundary condition while you are making integration for the derivative, partial derivative velocities, you need to, or you're going to find some functions of you don't know, so you need like fx and fy and etc. So you need some boundary condition sufficient enough to get what is this function is. And we also discuss about what is mathematical techniques if you have some difficulties while you are dealing with the integration and etc. by using the continuity equation. Okay, and this one is very it is the most general one. Okay, and sometimes you don't have enough or sufficient boundary condition because, for example, you are here having a moving plate, so you know what is the velocity here, it is fixed plate, you know what is the velocity here, etc. So you know a lot of boundary conditions. Okay, and then we discuss about the potential flow, which is describing the flow itself without taking in account the boundary layer or the effect of viscosity. And we neglect that is the boundary layer, it is way small if it is compared with the entire flow. Okay, and we start to say, okay, the definition of the boundary layer, so the definition of rotational flow function or rotational flow theory, that you can add any derivatives functions, which is either the stream function, the potential flow function, or the velocity itself. And this is a mathematical techniques, which is we prove it that is going to satisfy the continuity equation. And based on this, we know or we don't need that much of boundary condition because it is not related to a boundary condition. It is satisfied anywhere in the flow. So the constant which is coming out of the integration is can be zero because we don't care where is this flow is. For example, for this block, for we don't care if the block go up or go down or go left or go right because it is studying at the general case and we understand what is the techniques to reach to what is the solution. Uh, Once one with a lot of like if you have a pipe giving a water and you have a sink, there is no any boundary condition here. You will tell me, okay, here is this velocity is equal, okay, even the velocity is equal to zero here. Okay, if you put Navier-Stokes equation, what you are going to have? Okay, you will have a lot. It is not one direction. It is not one D flow. Uh, which is not which is mean it is, yeah, it is two-dimensional, but it's not two-dimension analysis, but it is not one direction flow as we discussed before in the Navier-Stokes equation. That is, we need to check if it is fully developed or no in city, and we need to reach to this point it is flow in one direction. Otherwise we will have a lot of W and U's and U's and V's, which is we can never solve it. Okay, so based on that, which is if it is not flow in one direction and you're trying to use it to solve the Navier-Stokes mathematically, no, don't do it. Go with potential flow. So if it is not one direction flow, go to the potential flow. So now we understand if we have a Navier-Stokes, It is one dimension flow, also one direction flow, use it with sufficient boundary condition. If no, go to the boundary condition. Okay. So we go to the potential flow, and we discuss later on about another techniques or another way, which is Reynolds Transport Theory, or it is an integral analysis, which is mean we don't care about what is happening inside. We care about the boundaries, what is going to have, or the system, the control volume, what is going to generate as a power, what is going to generate as energy, what is going to do as a forces, what is going to do outlet, inlet, and we don't care what is. If your problem is based on this, no, it is better not to use Navier. It is better not to use potential flow theory. It is better to use Reynolds transport theory, which is based on the analysis here, which is this one, which is generate the Bernoulli equation and generate the even the first law of thermodynamic and etc. And we understand how we can do mathematically, which is if even it is easy mathematically, and with some help of some definitions of physics of flow like coefficient frictions, etc. We can get or solve a complicated, for example, like this, a complicated flow. If we use Navier, it is a way headache. Yeah, it can be solved with Navier, by the way, because we know the boundaries, etc. But we don't care what is the velocity inside. If you remember, we was caring about, okay, what is the head here? You get my point? So, or what is pressure here? You get my point? We don't care what is happening inside. There is no questions about what is happening inside. So, no need to go in there. So here, Navier potential flow is a field analysis. Reynolds supports it is uh, uh, an integral analysis, and we understand the Reynolds transport change from the system to the control volume, and we understand what it means system. System is a closed system. Control volume, that is, you are taking a slice of control volume and checking this control volume what is happening, which is can be open and can be moving. Okay. Now we're going to discuss, and we discuss about the compressible flow. It is okay. Now we're going to return back to boundary condition. Boundary condition is a compilation of the potential flow analysis, because potential flow analysis didn't take into account the viscosity. So we can say from here to here, it is a potential flow analysis. But from here to here, which is very small layer, it is the boundary layer. So when we are doing the boundary layer, we are returning back to the boundary layer if our question is, what is the drag force? What is the friction force between the wall and the fluid? So if your question is exactly what is the viscous forces on the plate from the flow, and you don't care about the flow, again, you don't care about the flow, you care about the viscous force between the flow and the plate, and you don't have enough boundary conditions, or the flow is not one directional flow, or even it is one direction flow, but you don't have a lot of boundary condition. Like for example, you have an open stream, which is you don't have plate here or something, so you don't have enough boundary condition, and the velocity can go up or down. So at this case, you will solve which is above boundary condition with potential flow, and you will solve which is in the boundary condition with the boundary layer modeling. Okay, if you are interested above boundary condition, it is okay, use potential flow. But now we are going to concentrate about the boundary condition itself. The boundary condition modeling, which is defined, we already know that is a shear stress due to the viscosity. It is equal to mu du by dy. We already discussed it, and delta O. This is boundary layer height. By the way, there is a flow boundary layer and there is a thermal boundary layer. Later on, we're going to discuss it about what is the meaning of thermal boundary layer. Thermal boundary layer, just it is same concept of boundary layer. Boundary layer is its definition is where is the height of that is the velocity. If this one is velocity equal u, not so the height where is the velocity start to be 99 from the percentage from the U naught, which is mean it is almost become U naught. Same boundary layer. If this surface is, for example, 100 Celsius and the flow here is 25 Celsius, so the temperature start to decrease from to increase from 100 to 25, where it is 99 percentage from 25, it is the thermal boundary layer. And there is another calculation depending on Prandtl number and Nusselt number to define what is the thickness of the thermal boundary layer. We need to just concentrate about it. Later on, we're going to discuss it, like, because you need to compare between the thermal boundary layer and the viscous boundary layer or the flow boundary layer. And if the thermal boundary layer is bigger than the flow boundary layer, there is some techniques to approximate some solutions. And if it is less, there is another techniques to approximate. But we're not talking about thermal right now. Thermal will be later. Okay. Also, the shear wall, so is the stress. It is defined as CFX, which is local skin coefficient factor. It is just a factor multiplied by half rho V naught square. Okay. Uh, this is as a factor. يعني, it is a factor which is defining is the skin friction factor of skin friction coefficient, which is half rho v square. We know this is related to the flow rate itself and the forces itself. Okay, so multiply by coefficient, it is become what is yeah, for example, if you have a shape of an aerofoil, the aerofoil has a certain, let's say, CFX. So when you have a certain CFX from labs, from etc., we know now going to understand how to calculate it, so we can get what is the shear force at the wall. Okay. Okay. Of course, to get CFX, we need to get CW, which is mu, and at the wall, at d at y equals 0, so we can get CFX, getting CFX in x direction, which is mean CFX here is different than here, is different than here. You tell me why, I tell you C. du by dy here, cy is too much, and du is from 0 till u naught. Du here is too much, which is mean here is the slope is way high, here is the slope is a little. When you go more, the slope is a little. When you go more, when the thickness go, because du is constant from 0 to u naught. dy changing, which is mean here is small, here is big, here is big, is big, which is mean the slope change. When the slope change, viscous constant, shear stress or shear stress for viscosity getting decrease when you are going in the line, which is mean if this one getting decrease, this one is constant, this one is constant, so this one is decrease, so this one is function of x. Okay. This just to understand what is what. Okay. Now we need to discuss something else, which is the momentum thickness. Just bear with me. It is till now it is definitions. It is the thickness of the layer of the fluid, velocity v or u naught, for which the momentum flux is equal to defect of momentum flux through boundary layer. What is this? Imagine if you are going to have this actual flow. If you imagine that this one, it is like a, a non-velocity, because here is the velocity is equal a number, here is a 0. So imagine this part, if you distribute it like this, so this area equals this area, so you will get theta, which is momentum thickness. So the definition of momentum thickness, it is if you get the entire change multiplied by here, assume this one is a triangle, so this one multiplied is equal to a rectangular like this. Why we need to make it manipulation like this? It is very simple. It is equal in momentum, because imagine this one is giving an adverse momentum, so, and this one giving an adverse momentum, both are equal because the both areas are equal, which is this one there is no velocity and this one is no velocity. So you can say that is if I get this one, I know, and this one, see, it is all constant with certain number, it is equivalent to this one. So I can write rho u, u naught minus u, dy, u is the velocity, which is mean the change in the velocity, the change in the velocity in dy from 0 to delta, delta is a boundary layer, is equal to rho u naught square theta. Simple. So what is the momentum here? So you stop from u naught to 0 in a thickness delta, and here you checking the integration for the area. Simple. So you can write that is momentum thickness theta is equal to integration from 0 to delta u over u naught 1 minus u over u naught dy. This is for the stream, and this is very important. Okay, so this one, it is very important. We need to keep it. The momentum thickness, definition of the momentum thickness. Why? We are going, as you can see, 1, 2, 3, and with 4, I think so, 1, 2, 3 only. Okay, it is a steps. At the end, we need to get this one. We need to get an analysis. We need to get numbers to make an analysis for the friction here. We need a formula for this. We need to get all of this. To get it, we need to use that definition. Okay. I know this is step number 2, but I am not going to discuss why we are doing the steps, but just bear with me. We know that it's the shear stress, mu du by dy. Okay. And this one at the wall. And we know that is the shear force also equal O u naught square d theta by dx. Okay. By the way, d theta by dx, it is the same, because it is the change in theta and the x, because we understand this one will go more, the area change, so theta in the x change. Okay. Okay. And if you try to make the derivative of d theta here, by dx, and you write this one, and you will put this theta, you will reach back again to du by dy mu. Okay, it is just a manipulation of mathematical manipulation. Okay, but put it in your account. Then we need to get that. Oh, it's okay. This is the mathematical route, or way to try to define what is delta, what is cfx, and etc. We will go with it. Okay, 1 second. But I need to put the definitions. Okay, there is the displacement thickness. The displacement thickness, which is when we have a change in the u from the wall till here, the potential flow seeing this area as a block. So the stream start not to be potential flow. No, it is getting affecting with another effect, which is going the stream going to bend like this, then it will continue normal. This bend is named displacement thickness, and originally this displacement thickness for the potential flow above is less than the thickness, the boundary layer thickness. Okay, why we need a displacement thickness to define it? Because displacement thickness is changing the conditions in the boundary flow, so in the potential flow, or in another way, it is another thickness which is reduce the area which is the flow is running, which is increasing the velocity. Okay, so now we need to define what is this displacement thickness. The displacement thickness, its definition is if you make integration from 0 to delta, rho u naught minus u, okay, dy equal the displacement thickness itself, which is here from u to u naught in dy from 0 to delta. This is how much it is equal to displacement. So displacement thickness, um, it is an integration from 0 to delta 1 minus u over u naught dy. Okay. This just an example. It is better to get it because later on we are going to concentrate about here only. Okay, but this is for you if you're doing like a simulation or for example for a wind or a wind tunnel or you're doing CFD in a wind tunnel, and you need to define what is the environment limits you need to define for. If you're not taking care or you don't care about the viscous force, I don't care what is going to have the viscosity or the shear on the floor, whatever, but you care about the flow itself. So you need to take an account to simulate correctly. You don't need you do you want to absorb that increase in the velocity to get an accurate result. For example, in wind tunnels, they are designing the wind tunnel with a diverging wall like this, of course from bottom and from top, or sometimes from bottom only, to increase the area of the flow based on the increase of the displacement thickness. Of course, the displacement thickness it change over the x, which is mean it's going to be increased when you are going to increase, okay? Because the boundary thickness is increasing while you're moving, so the same is concept, okay? So if you want to know what is the area at the end needed to be, so you need to ask yourself, what is the velocity which is I need to know, and what is the displacement thickness. It is very simple. After you make that integration, you will get the displacement thickness at this certain point. Here you can u by u naught, okay? Uh, at here, of course, u is at here, huh? Over u naught, u at here over u naught, etc. So dy, you will get displacement thickness. When you have the displacement thickness, it's very simple. You will add the displacement thickness up and down, so you will have more area, so you can write uh, what is your okay, what is your uh, what is your total head, okay? It is just to identify about it, okay? But however, now let's return to the most by the way, if you are going to neglect, if you have like a CFD or something, I want to neglect all of this, for God's sake, try to take the environment way, way bigger, which is the delta thickness, or it is neglected. You get my point. Yani, we do it in the tunnels, wind tunnels, because the wind tunnel, it is in confined space, and we are doing scaling of the model itself. But if you're going to do a CFD with an actual size, you can neglect this one with taking a big environment sufficient enough, okay? But it is needed to be known because when you're doing CFD and somebody coming to you and giving you a report from a wind tunnel, you need to understand What is the condition? Is he done something wrong or no? We're going to discuss this point uh, in tests, probabilities, and all of this to to have a judgment about the result you're getting from labs, comparing it with CFD. Okay, and to criticize, okay, is this result from lab taking into account some conditions which it needed to be taken account, but yet they didn't take it, or which one more accurate is UCFD or the test itself? Okay, something like later at the end we're going to discuss it. Okay, now we're going to return back to here. To define at the end, we need to reach what is delta in time of x. Okay, what is a function of delta in time of x or in function of x? Because if we know delta in function of x, we agreed that is we can get cfx. Again, if we know delta as a function of x, we will know cfx. This is very straightforward. Okay, let's go. First, you need to define or to plug theta, which is the momentum thickness formula. Second, you need to identify that the shear stress from viscosity on the wall is this one. When you are applying y equals 0, then you need to make this term is equal to this term. This term is the derivative of this term in x. Then you can manipulate it to get the delta by del x. When you have del delta by del x, you can make the integration or whatever integration, so you can get the delta for x. When you have the delta for x, you can get the cfx. Okay, this is always the standard procedure. Okay, so let's go to an examples. Uh, Before to go to the examples, we just need to understand another point that how we're going to get the CFX when we know the delta in function in x direction, because CF is CFX integration from dx to 0 to L1 over L. You will get the full CF. And if you write the formulas, so and you know CFX is equal to all of this, so you can get what is the CFX. Okay, we are going to turn back to the correlations, because after we finish, uh, we can understand what is this correlations, which is a function of delta in respect of x. For example, here in laminar flow, delta is equal 4.91 divided by Reynolds number in x. Uh, Multiplied by x, of course, as number x is rho u x divided by mu, or u x divided by gamma. And Reynolds number at the full length is rho u L divided by mu, etc. And in case of a plate flow over a plate, Reynolds number, if it is bigger than 5 multiplied by 10 to the power 5, it is a turbulent flow. Just a definition, what is the difference between turbulent? But we're not going to discuss about this one. This correlation, it is uniform upstream, which is mean the flow here is uniform. Okay, so this correlation is built on a uniform upstream. So if the upstream here is taking a shapes or like a parabolic, or coming from a, a, a floor which is already having a friction, then it will go to the airfoil. So this is not applicable. Okay, however, we can approximate it with some of cases, but this only if you have a uniform upstream. Okay, now to understand, let's go to an example. I will not talk about separation. It's very important, but we need to take one example. Then I will return back to the separation uh, analysis, or what is the definition of the separation, why it is very important in the CFD, and you need to check it. And this is the questions which is you're going to have when you're doing the CFD. Is there a stall? Stall is meaning separation. Okay, stall, when you hear it, for example, airplane, the airplane stop to have a lift because of stall, which is mean separation. Okay, but let's take an example. It is a very simple example, yet it's going to help us. Imagine that you have a uniform flow and you have a belt rotating like this, and the uniform flow is going in this direction. So the belt is rotating with a velocity of ub, and the uniform flow is u naught, and they define to you that is ub of the belt is equal half of u naught. And of course, they told you uh, the start of interaction, even they don't need to tell you, but they told you the start of interaction between the velocity flow and here is boundary layer is equal 0. Okay, and they start to give you the function of u in definition of course, u equal u naught multiplied by a plus by over delta plus cy over full of delta square. I will not go in detail how they got this formula. They can get this formula from Navier. They can get this formula from whatever. Okay, but now, while you have this formula by any method, for example, you done a wind tunnel test, and from the wind tunnel test, you got measuring the velocity in each one, and you got this formula. But you know there is some parameters a, b, and etc. going to change due to the change of the shape of the belt, the shape of the tunnel, etc. However, you got the formula. Now he told you we need to get a, b, and c. We need to get the full formula. It Then you will start to put the boundary condition. This is the first step, by the way. Because the easiest way is to put the boundary condition. So you know at y equals 0, u equal ub, which is equal to half u naught, because the velocity here is not 0, is a number with ub. Then you can plug the numbers, you will get a equals this number. Okay, at y equal delta, anywhere, you know that is u equal u naught. So plug the numbers, so b plus c equal half. And the third condition, we already used something like this, which is there is no friction while there is flow inside two tubes. And we said that is if there is no friction anymore, we can write that is du by dy equals 0, which is at u equal delta also as well. So du by dy make derivative for dy, and you will get this equation at y equal delta equal 0, so b equal minus c. So if b equal minus 2c, so b equal plus 1, so you get a, b, and c. Voila. Okay, so we can get a, b, and c just with the boundary conditions. Okay, now while we have the function of the velocity, we can start directly to the steps. Momentum thickness, u is a function multiplied by 1 minus u over u naught. I just put the same equation here. It is all multiplied by dy. Make algebra, left and right, right and left. What we done here in algebra, just to understand, I just tried to keep it in a way of a plus b multiplied by a minus b, just for simplicity. However, you can do any complicated method like this one multiplied by this one multiplied by this one multiplied by this one, plus this one multiplied by this one multiplied by this one multiplied by this one, plus this one multiplied by this one, etc. But I try to, like save a little bit of terms. So I just divide it like this based on this. A plus b multiplied by a minus b is equal to a square plus b. So just to make it easy for me. However, you will reach to, both directions the same. You will reach for the same, make integration in y. You will take this one, apply it from 0 to delta. You will take this one from, so this is the equation for momentum in thickness in respect of the boundary layer thickness. You can put the sigma outside. Sorry, the delta outside. So when you have the delta outside, so theta equal this numbers, which is 7 delta over 60. Good. The next step, huh? What we agreed? We agreed that first, momentum thickness. Second, we need to use shear wall. Oh, the shear stress at the wall. Mu du by dy again. So we know that is du by dy equal. We already just done it, by the way. Huh? We just done it here, but not equal 0. Huh? But we done the derivative of du by dy. So write the derivative of du by dy. It is equal this. And we know a, b, and c. So you know this equation. Multiply it by mu. What you will have? You will have the shear wall. Here. So mu multiplied by du by dy. You have the shear wall. And this one is equal to this one also as well. So when we apply shear stress at the wall from this equation, multiply by mu, while y equals 0 at the wall, so it will be, this term is 0, so it is u naught 1 over delta mu, which is u naught mu over delta. Simple. Then apply the same concept, that is the shear wall is equal to rho u naught square d theta by dx. It should be equal u naught mu over delta. Then we can write it, that is d theta by dx equal mu over rho u theta, so u naught by delta. And we know that is delta is function of x. We know delta is function of x. So when you make the integration, don't say, so it is mu over rho u naught delta multiplied by x. Wrong. We know that is delta is function of x. You remember we done some manipulation concept like this before when we're dealing with continuity and equation and Navier Stokes, and we said that is because we know dB by dx, if you remember, is a function of x, and we are going to manipulate the continuity equation to get the dx away and to deal with. See, we'll do the same mathematical manipulation. Okay, so d by dx for theta is equal to, I didn't do anything, huh? D by dx for theta is equal mu over rho u naught delta. I didn't do anything. What is theta? What is theta? I know theta is function of x or function of delta, right or no? I know theta is function of delta, and I know delta is function of x. So write theta equation, which is 7 delta over 60. Then 7 and 60 is constant, put it outside. So d delta by dx equal mu by rho d naught. Always we're going to do this technique. Huh? So now you can put dx here and d delta here. So now you can do the integration. Before you cannot do integration in theta and delta and x, but delta is function. Now you can do the integration. So d delta and delta is here and dx. Before you cannot do it because if you do it, you have d theta here. You get my point? So you cannot make the integration. Okay. So delta square over 2 equal, this is all is constant, multiplied by x plus constant. Okay. Which is, you can state it that, or you know that one boundary condition, always we're going to do it, at x equals 0. This is the start of delta, which is delta is equal 0. So it is very simple. Put x equals 0, or this term is 0. Delta is equal 0. So c equals 0. Simple. So delta square equal this one. So delta equal 4.14x over Reynolds number of x. What is this? This is the equation of delta in respect of Reynolds number and x. You remember here when we discussed this from where they got the formulas? It is the same concept. They are making wind tunnel tests, and they got the equation of the velocity, because they will measure the velocity everywhere doing this mathematical manipulation. Then they got this equation. Then they can say, okay, if the shape is a plate or the shape is a belt, delta equals this number. Okay. Of course, mu over rho u, it is 1 over rex. Okay. Okay. Now we need to get CFX as we agreed. We got this one. We need to get CFX. Very simple. Shear stress is equal to CFX 1 over. Simple. Okay. And we know also the shear stress is equal what? You know what? Mu over delta. Aha. Now we have a delta is a function of x. Yes or no? And we get all of this. So fx is equal to mu, you know, divided by delta multiplied by o over half rho u squared. U squared by u. So this one, small manipulation, algebra. Then cfx is equal delta, remove delta and put it in respect of of this equation. So you will get that the CFX is equal 0.483. So now we know what is the coefficient of friction. What is the coefficient of skin friction for that shape? So whatever I'm going to change in U and the density of the flow, it is grease, it is oil, it is water, whatever, I know this one in respect of where its location in x direction, because it changed. Shear stress is changed from point to point. Okay, so I can write even this one. Sorry, I can write even this one, which is CFX is equal a number. It is from correlations, by the way. It's okay, but this overlap it. Okay, and they calculated, they done the same concept to get, we got even theta is a function of rex and etc. Okay, because you have theta as a function of delta and delta as a function of rex. So okay, now we need to check what is the entire drag force. The entire drag force. Okay, if you need to get the entire drag force, which is mean you need to make the integration of cfx for here and here and here and here and here and here, which is decrease, 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 and you make to do it for the entire plate of L. We need to make CF is equal 1 over L, integration from 0 to L, CFX dx. Okay, we're going to do the same. If we need to get the average, the full one, so from x equals 0 to x equal L, same concept, CF, put the equation of Reynolds number, please. Here put the equation of Reynolds number. Please write Reynolds number in its form of x. Simple. Okay. Reynolds number in its form of x, it is it will be, of course, this one will go out. This should be in Reynolds number of x. Then it will be this integrate. Of course, here's power to half. By the way, I'm going to correct it here, because Reynolds number of x under root here is power to half, but I didn't write it. However, this also power to half. I didn't write it. However, it is written here. Yeah, it is written correctly, because this is power to minus 2, minus 1 over 2, half, minus half. So plus 1, it will be power to half. Okay, but يعني the solution is correct, but I forgot to write half. Okay, then you will get the function of CF, okay, which is voila, which is equal to a function of Reynolds number total because it is mu over rho mu. So you can write that is tau average is equal to CF, which is this tau multiplied by, oh sorry, this tau multiplied by half rho v square. Of course, if you multiply by half and rho and u square, you will get rho and u and half of this number is this number, by the way. Okay, and it is multiplied by mu. I don't think so. Mu is right. Ah, sorry. Half of this number is this number, and this term is 1 over root RL. So you will have this formula. Okay. Now, while we understand uh, such example, we will return back to understand or to the table. So after doing some manipulation like this, while they are getting the velocity function, they can write all of this. And now we need to define something that is the drag force is always due to friction and due to the drag itself, to the pressure. So when you are checking the pressure, for example, you have aerofoil, so the cross section, the maximum cross section, multiply by the drag coefficient due to the pressure, half rho u square, and due to the friction is the parallel surface multiplied by u square or CF, and this CF what we are calculating based on the previous techniques. Okay, if you have very thin plate, you can assume this one is equal to 0. Okay, this point also just for you, that is y over delta from the before. You can see the change in u over delta and the change here. So, which is means the laminar flow giving more shear force, by the way. Turbulent flow giving less shear force. So they will tell me, okay, it's better to have a turbulent flow if I don't want the shear force and I don't love it, etc. Wait, turbulent flow have something very dangerous, which is the separation. The separation, if you applied Navier-Stokes equation, you study on the wall, same concept, etc., the use and whatever, as we discussed before. So wall condition is du by dx is equal 0. It is just some work of Navier-Stokes equation. So why I'm trying to write it like this? If you have, for example, a flow, and when you are going in the flow, there is high pressure here, like you have uh, a diverging duct. So the pressure is increasing and the velocity get decreased. Sometimes the pressure at the wall here is higher than or very high, that is create a reverse flow like this. Okay. So when you have here's the derivation is what when you have d del b by del x in a positive is a positive. So this number is a positive, which is mean delta shear stress by del tau is a positive, which is this one, which is mean if there is a chance to have a separation. But it's not meaning all positive pressure going to create separation. You need to be a little bit higher. Let's see the examples. If you have du by nu by dx, okay, no. This one, see, if you have no change in the pressure, so dB by dx is equal 0, it is 0 gradient, no change, everything is okay, there is no separation. And the BI or the center, if there is a separation, BI is the center of separation, but it is on the wall. Okay. if you have dB by dx is bigger than 0, it is weak adverse pressure, yet du naught by dx is less than 0. Du naught by dx is less than 0, which is mean, as we agreed here. So still no separation, but here, which is the change in du by dy, is almost uh, in the flow, and shear wall is not equal 0. The shear stress at the wall is not equal, it's equal number. So, but if I have a critical adverse separation, which is mean I have higher and higher dB, so here, like here, the shear wall here, the shear stress is equal 0, because still du by dy, del y by dy becomes 0, because the flow start to make like this. Yani before, the flow is like this. Now there is a pressure, so the flow come like this, which is mean there is no movement just here at all in the flow, which is there is no viscosity between this one and the flow and the plate, which is means there is no shear anymore. This is the critical point. If the pressure increases at that critical point, which is du by dy equals 0, if the pressure increases, so it will be a backflow. While you have a backflow, stall happen, which is mean you need the flow rate velocity effect is like this. When you have a backflow, swirls will happen. So, for example, for the uplift is bye-bye. If you have a bump, so and the impeller of the pump is pushing the water, and when you have a separation, the velocity difference, which is you need it, which is velocity difference, as we agreed before, it is equal to the forces going to happen. We agreed like several examples before. If I have V in and V out or whatever, if I'm going to change that is the delta V's, I'm changing the velocity, the forces. If I change the forces, so or reducing the force, when I'm reducing the force, there is no enough power I'm injecting it while the impeller is rotating. So this is the dangers of the turbulent flow. Okay, this one, it is just to get it. When you do CFD, you need to check in the boundary layer is there separation or no. If you are really concerned and you're going to advise there is a separation, and one of the advice which is you can make, like if you have, for example, a plate like this and a plate like this, which is the area here is a small and the area here is a capital, and the flow it is going like this and the plates are rotating like this, then you find a separation, which you find it swirls here like this. You're going to advise after doing the CFD, reduce the area, because while the area is reduced, so the pressure here will get decreased, or increase the number of plates. Or we're going to discuss it when we go to the fluid machinery, by the way. But this is how we need to think and how we need to give an advice as a CFD specialist. Okay. Okay. Now let's return back to examples, because we have example 2 and we have example 3, and that's it. It is not a big deal, by the way, but example 2. Example 2, it is defined as it is a laminar flow in a tunnel, and the tunnel is taking that shape, and this is the upper wall. We don't know what is the shape of the upper wall, but they're telling you we don't some. Okay, and the curve t to rotational flow is varies. We agreed about it. Huh? We agreed here, huh? When you do the tunnel, that is the tunnel shape is changing due to displacement thickness. Okay. So now we understand what is his concept. He's saying that is I need, for example, I do a CFD for my tunnel. You get my point? To define what is the upper wall, for example, or anything else, okay? But he's telling you I have a wind tunnel. It is a laminar. I start with laminar flow, and the wind tunnel upper all is changed to the curve is to keep the rotational flow is varies. So he's trying to tell you, or he told you, that is u naught is equal to a multiplied by x over 1 over cube, and he told you that is a is a constant. Okay, so now you're going to tell me, okay, so u naught, while I'm going to go forward, you're not going to change. Why? Because the area change. The area is going to change. So because the area is going to change, he knows if I put, for example, 100 cubic meter per hour or per second, why the area is reduced. So if the velocity here is equal, u naught is equal, blah, 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 here it will be something else. Based on what? Based on the equation of change of the area. This not area, this constant. Huh? So he start to tell you, okay, the velocity going to change with this one. Even he can tell you what is the area look like here, and you can get this equation. Okay. So now we need to, and also he start to tell you, I already done a test, and I already know that is u, I measure it, while it is changing in the y direction, it is taking this function multiplied by u naught, and displacement thickness divided by layer thickness is this number, and theta is this number, and this after he done test results, he got all of this. Okay, and he told you even like uh, boundary layer thickness is b is constant divided by x over n. Okay, and he gave it to you. He done a test and he give it to you all of these results from his test from his one panel. Okay, okay. How we got the delta? How we got it is we already discussed it from the test or from the velocity cycle. Now, okay, where's the question? So the question, by the way, he need at the end to get CFX always, always who done the wind test, he need to get CF and CFX to put what is the coefficient friction for his wind tunnel and in X, in each X, and what is the total coefficient friction. This is what he's trying to get. Okay. Of course, by the way, he can tell you this is constants, and you can put it with boundary layer. You can get the constant. However, he give you the full equation. Use the same. But now, by the way, we already have the equation. But if we don't have the equation, same procedure. Yani he just make it easier for you. But if we don't know the equation, Habibi, put the equation, du, you have the equation of u, integrate, put, get it. After the integration, you will get some numbers. This numbers is in y, apply from 0 to delta, you will get this one. So if he didn't give you this one, you can get it from this one, okay? But he's making your life easy, okay? So we have that equation. Good. Let's return back. What is the steps? The steps is after you get this equation, shear wall at y equals 0 for this one from this equation should equal this equation, mu du by dy at y equals 0. So make the derivative of u in terms of y, apply 0 equal to rho u naught d square d theta by dx, and we need to manipulate to get dx aside, d theta converted to delta, and make the integration. The same standard procedure. Okay. So this term equals this term, put it, make the derivative. Where it is? Yeah. But now take care. Take care why? Because u divided by u naught is a function of x as well. Okay. Just take care about this point, which is will be du by dy, derivative of du by dy. It is 2 over delta minus 2 y over delta square. Why it's not written like this? I don't know. By the way, and it's just mu ax cube. It is u naught. One second. Ah, so I get confused. So du by dy, yes, it is u naught 2 over, as is written here, u naught multiplied by 2 over delta minus 2 y over delta squared. So du by dy, u naught is equal ax cube over 1 over 3. This term, so this term should equal to this term while you apply at y equals 0. So this term is by, so it is mu, this term 2 over delta equal to rho mu naught square. Of course, this one with this one by d theta by dx. D theta by dx give you theta, but we know theta in terms of delta. We know that we're taking the technique to get dx d by dx in the delta and write the theta equation in delta. Okay, same technique. Theta equation in delta is this one. Put it small algebra, that is delta aside and d delta with it aside and dx aside, like this. Then you will have this formula after you make the integration with delta x plus c. Apply the boundary condition directly. At the start, it is 0, 0, 0. So 0, 0 is equal 0. So delta is equal to this one, which is, you know, delta is equal a function of x. So compare it, please. So you will find it is a constant, which is b. And this power of n, it is equal 1 over 3n. So b is equal to this one, and n is equal to this one. Because we know that is mu equal gamma multiplied by rho, so delta can be written like, it is just an manipulation, because usually we are trying always to get our results in Reynolds number. Okay, so based on this, you can write 45 gamma over area. So you can write that is delta multiplied by this one, which is delta is equal by this one. Okay, which is A is equal to the uh, the area itself is a function of x, if you remember. By the way, from where we get the area, it is very simple, huh? Because we have this one, and the area, etc. Okay, which is here. U naught equal sorry, A is not area. Sorry. So A is a constant. I got a little bit confused. Okay, A is a constant itself. It does not the area. Okay, so delta equals to when, just like this. Remove A, put it in its term, then etc. till the end. By the way, why I get confused? Because there is no area, by the way, huh? There is no area. There is no area. Because when we open this one, it is A as a constant, not as an area, when we put it in. Okay, so when we plug the numbers, we need to return back the A. We don't want the A, we need it as a function of u naught. So when you start to manipulate it again, so we'll find it that is d over so delta over x, because delta over x, it will be x minus 2 over 3 Try to manipulate it, try to keep an x under the root. We are trying to get the form of Reynolds number, by the way, and changing the x power outside. That's it. Okay. So at the end, after algebra, you will find that is delta over x equal some number over Reynolds numbers root. So CFX equal to the same concept as we agreed before. Tau first equation equal tau second equation from here. If we need to get the CFX, so CFX to get the CFX, this equation should equal to the second equation, like what we done here. For where it is, okay, here. To get the CFX, we know that the tau is equal this formula, CFX, and it is equal to this formula as well. So just equal this formula as well. Okay, which is from 0 till u naught, which is du, which is du naught, divided from 0 del delta, which is delta, which is du by delta by d. This is du by dy multiplied by mu. Put this one equals this one, cfx equal blah blah blah. So it is the same concept. So we know that is this one is 2 mu u naught over delta equal, it is just the same manipulation. So you will find 4u by the delta equal. So it will be 4 gamma Rx. It is algebra. Okay. So you will have terms of CFX, of course, is what is happening here. It is just the manipulation because we need to get it in the terms of the Reynolds number. It is 4u multiplied by this term. You see this term with u naught and x. It is Reynolds number inverse, and this one is Reynolds number. So this one by this, so it will be root down, and this will be black the numbers, and it will be like this. Okay, just manipulation to get it. Why? Because we always have a term, always delta by x, Reynolds number in the base. Same concept, Reynolds number in the base. You need to try to get CF. CF is very simple. You can put this number directly. So this number, but you need to break the REX to make the integration in X. Okay, so it will be like this. Put the integration, make integration in terms of X from 0 to L. Then you will get this one. Then you try to manipulate it a little bit to get in this term like 1 over root of REX, REL. So you'll get this number. So like this, we can get what is the total coefficient of the average coefficient function for the one tunnel and for the walls, and also at x at any x direction how much, and we got also b and n is how much. Okay, till now it is little bit this was the easiest one. He give us the equation or whatever. Here it is more easy, but we start to identify that is u naught can be not constant, not like before. Then we'll go to the more complication. We know it is u naught is not constant, not due to the plate, not due to the tunnel, because like for example, it is a wind, it is coming turbulent flow at end. It is coming like this, and this shape is going to have a friction with this shape. Now it is way complicated, which is we understand that is the wind itself having a friction with the wall, so it is taking this shape. So u naught is taking this shape, even it's not taking a function, it is taking this shape. Okay, and it is going to have a reaction with the plate. Now we need to ask ourselves, what is same procedure. We need to take the coefficient, the forces going to happen acting here, etc., etc., etc. Okay. Before to start such, you cannot make two solution and two, yeah, you cannot get the CFX and CF for the wall, for the floor, then after to apply here, it is cannot be solved. So we are going to go back to the correlations what we know. The correlations what we discussed to define the wind itself, because we're not going to design the wind itself, but we need to get what is its equation. So the correlations is depending on either laminar or a turbulent. Or for the turbulence, there is one method. It's named 1/5 law, and there is 1/7 law. It is not. It is an approximate. By the way, if you plug the numbers, you will get the same numbers. By the way, if you get, for example, here it is Reynolds number, if it is turbulent, it is 10 of power 5 multiplied by 10. Let's assume it is 10 of power 6, and here is 10 power 6. You get this number, you get this number, you get the same, by the way. It is a way of correlation. It is done by experimental, how much we'll get. So you can take all of this based on you're going to decide I am going to use or to follow the seventh law for turbulent flow, or the seventh so a fifth law for turbulent flow. For laminar is laminar. Okay, so now like this we don't need to design or to get a mathematical calculation for the wind itself. We can use the seventh law, and this, by the way, when we're doing CFDs, we can use based on this. We need to take the CFD for the wind on the building, and the wind itself, we can define it based on the seventh law. Okay, so he told you, based on the seventh law, that is U equal Y is the maximum U, what you have, U equal Y, the maximum U, what you have, multiply by Y over delta. This delta, what you're going to have, okay? It is power to 1 over 7. If fifth law, 1 over 5, okay? So we need to know this one, okay? Okay, okay. Let's go step by step. So the study is a case, just it is a definition. We need to know. We cannot identify, for example, here going to be a friction due to viscosity, but here is the uy is a function of the seventh. So if you need to take the full one, so you need to take du to get the full one. You get my point. So u here is a number which is going to change why it is moving in this direction due to the boundary condition, and the boundary layer vertical on the sheet on the paper now is going to increase the boundary layer thickness. Okay, so we have a lot of variables going to be happening. The good point about the mathematical and the integration, it is doesn't care how it is, because it is using the equation itself. It's using the general forms. Okay, apply the same. We have theta. Theta is equal what? Simple. Again, return back. Theta is equal to the function of u, whatever is the function of u, divided by u naught, multiplied by u over u naught. And u naught, so u naught, it is, 1 second. So what is the function of u? The function of u divided by u naught, which is u infinity, it is this one. So because of the seventh law, I don't care what is the function of this one, what is the function of this one, and no, I already know what is the function, the fraction between that function and this function. It is y over delta power of 1 over 7th. Okay, so put put make the integration, get the equation in terms of delta, voila, repeat the one, d theta by d. So let's, okay. So we know about this one, d theta by dx. We need to get the dx aside, then to put the delta here, same manipulation, same blah, blah, blah. Then you will stuck y, see. Now we cannot continue with the same procedure. Why? Because we have u naught. U naught itself is a function of u and delta, y and delta, and u naught also itself is a changing in this one. So now, not like here we have a fraction with an equation. Now we have the u naught itself. Okay, so even if we know theta is equal what? Yes, still O u naught and write d divided by theta. It is the same concept. But we cannot continue and write the equation, which is the same procedure which we discussed, like mu du by dy is equal to d theta by dx, like what we done here. If you go to the example, when you have du by dy, if you have the term of sorry, the term of theta, du you know it before. We say this is du is u naught minus 0 and dy is delta minus 0, so it is u naught u delta. Now we don't have that case, okay, or the u naught itself is changing, so we cannot continue with the same manipulation because the u naught itself is changing. Okay, what we need to do, we will reach to that this term we know, but we will use the other one, which is half vfx rho u naught square over 2. Why we use this one? Because du itself, it is, or the u itself, it is depending on this function and depending on this function and also in vertical. So I don't want to use u. I'm trying to run away from u. U, it is an upper function, is different than the u in this function. Okay. So okay, tau y equal what again? Oh, okay, it is equal cfx over 2 or u naught. I know u naught is going to change, but it is easier than u. We don't know u over the plate. We don't know u over the plate. It is clear. Now, while he told us we are going to use the 1/7 law for the wind, okay, I am going to use also the, for example, the 1/7 law, but I cannot use it because we said that it should be uniform. So we are going to use one theory or one, there is one Prandtl. Prandtl, he derived that cfx is this function for Reynolds number 1 over 6 in x or in delta, يعني, which is mean r x in delta, in delta is this number in cfx. It is a long derivation, but it is an entire formula which is you can depend on it. It is Prandtl formula. Okay, that's why I told you it is very complicated, because we are going to use some formulas from the textbooks. Okay, based on this we can write cfx in this term, and based on this we can write that this term, which is the cfx, is equal to 70 delta dx. Okay, simple. Why? What happened? By the way, u naught square by naught square rho by rho. By the way, so it is just remaining 2 here, which is gone there. So this is called like this. So I know Reynolds number at delta is equal to this one, which is, you can write d delta because you change from theta to delta, and there is one here technique which is has been done, is because we know that is our Reynolds number at x is this equation, and Reynolds number at delta is this equation, which is mean you can manipulate. So based on this definition, of course, here it is, I don't know in the scan why it is missing, but add text. This one is D, so it is in blue. It is D R E X multiplied by multiplied by 9.72. Okay, from where we got this one, 9.72 is the 9.72. Okay, so from where we get it, okay, this number is this number. Here is x. Okay, so it is d delta by dx, d delta by dx, this numbers by 2, it is this number, it is equal to Reynolds number, blah, blah, blah. Okay, we know that is d delta by dx. If you make derivative here, d delta and dx divided each other, it is exactly divide this one by this one divided by this one. So all of will by, so you will get d delta by dx. It is d Reynolds number at delta divided by d Reynolds number at x multiplied by this number. So while you have this one, so the definition of Reynolds number in delta perspective is multiplied by d Reynolds number in delta is equal to d Reynolds number in x. So voila, you're going to have, after the integration, so you will have 0.16 Reynolds number of x, which is delta. So you get a formula from Reynolds number at delta in respect of x. Okay, plus c, apply condition. If when you apply the conditions, c equals 0. So because you know here the delta will be equal 0. Okay, so by the way, delta here is the height, and we are writing here always delta dash. Delta dash is not this height. Delta dash, it is the vertical over the plate. Okay, to segregate between delta and delta dash. Okay, just to identify what is the difference between delta and delta dash. Okay, here is dash dash. Okay, so from this equation, while we know that is Rx is like this, R delta is like this, which is mean, and if the two in the same equation, so x to this power is equal to this one. So delta dash is equal to this one. Okay, which is you can get an equation of delta dash over x, and you can get delta dash over x in the respective of Reynolds number. How we got it in respective of Reynolds number? It is so like this, because we know that is delta, we name it like dash or something, or just to differentiate it by x. It is this equation, which is no delta by x is Reynolds number for delta divided by Reynolds number of x based on this approximation. Okay, still we always need delta to be written in a function of Reynolds number of x, right or no? Yes. So how are we going to do it? See, Reynolds number of x over 1 over 7, because it is like this. It is the same if we kept it x over something x. How? This is x over minus 1, and this is x over 6 over 7. So in total, it is x over x power to 1 over 7. So this term is equal to this term. Okay? Because this term is equal to this term, and we know because this one is x and this one is x, so we can remove the x and put the x's put as Reynolds number. Okay, clear? So of course it will be 1 over 6 from here, because Reynolds number is equal to the x, so x over x. Okay, based on that, CFX is this one, because we already have the, we need to get the CFX formula. CFX formula, it is based on, where it is, yep, here. So CFX formula, remove Reynolds number of delta and put in expression of Reynolds number of x. Okay, very simple. So it is Reynolds number of delta as here, this Reynolds number of delta, and which is equal this term, all to power of minus 1 over x. This from this equation and from this equation. Okay, very simple by the way. Okay, so this equation, yeah, even by the way, even this manipulation, it is not going to affecting defining the effects by the way, but it's just to way to write in terms of Reynolds number x. So Reynolds number of delta and x, put it here, voila, you will have CFX in relation with Reynolds number of x. If you have a Reynolds number of x, remove it, put the equation of x, CF integration, cfx dx with the integration, do the integration from 0 to L, and when you do the integration, you know this is the result of the integration from 0 to L, then you know that the shear stress is equal half Cf for U. If you apply the number, which is you have half this one and half and rho etc. and 7 over 8. If you put all of this, you will find this number, which is U, the velocity, which is U infinity, 13 over 7, U 1 over 7, rho 6 over 7. So this is a full shear force you're going to have. And this one, the CF is as a definition. If you start to plug the numbers. So if you want to calculate the force, the drag force is shear stress multiplied by the area. And the area, you know, it is L by delta, but not delta dash, huh? Delta. And you know delta is it is changing because we studied in one general case, so multiply by dy. So it is an integration from 0 to delta, multiply by dy. Write the equation, u infinity, this in term with u infinity, divided by dy. This is all constants outside, make the integration, then the case it will be like this. It is just the integration, make the integration in terms of y, 1 over 7, etc. Then you will find this 1 over 7, and at the end, if you try to get the entire force, it is L here. This one is L over 1 over 7, which is this L. Here is constant. So this is force when at, because you're making from 0 to delta. Okay. So if you make the integration, which is force 1, it is this number, delta, etc., etc., etc. And force 2, it is like this, then equal. What is mean by force 2? This one from our derivation, the blue one from our derivation. So if I want to compare it, what in case if I have a uniform flow, for example in CFD I apply there is a uniform flow, what will be the force? The force will be as a calculation a uniform flow, which is mean there is no change in the velocity in respect of y, so it will be 0.135 delta until the end of the equation, which is mean this term is bye-bye, which is this term. So uy equal u infinity. If this term equal 1, so remove this term please, make the integration, which is from 0 to delta, it is a delta. You get my point? So if this term is 1, so the integration is delta from 0 to delta, so it will be just put the numbers, etc., etc., etc. Then you will find one equation. If you divide the two equations, you will find that force, which is actual, divided by force, if we assume it is uniform, it will be 10 multiplied by delta over 3, which is mean, for example, if I have a height here of a building with 10 meter, and I done the CFD simulation, so it will be 100 divided by 3, it is almost divided by 3, it is almost 33. So it will be 33 times difference in the force. got it? Which is mean this force, it will be bigger with a 33 time, okay? Which is giving us an indication when you do CFD analysis, take care about these conditions. It is really going to affect, okay? Okay, I just corrected some. This one is power 6 to 7, which is by mistake, and it is the integration to be multiplied by 7 over 6, so this one is wrong also as well. So we're just going to keep like this and like this. Okay. So based on this one is 0 0.015 and this one 315. I'm just correcting the numbers. And so F1 equal this term 6 over 7, and L here also it is the same concept, okay, 6 over 7. It is also 6 over 7, okay. So this term is the same. If this one is equal 1, this term will be the same. If this one is making the integration, 7 by 7, it is 49, and 13 plus 1, so 13 over 47 plus 1 in the base as an integration for the delta. You will find is of course this one will be divided by this one, so it will be the same, because this one will multiply the same, so it will become delta at the end. So this one 1, not this. So if you divide f1, which is based on like this, divided by f2, which is if it is fully, of course if it is fully, more friction. If it is like this, less friction and less force. If you divide it all together, you will find that f1 divided by f2, it is 49 by 62, which is, in case of uniform flow, there is around 26.5% increase in the friction force, or the viscous force acting here for the plate itself.